Alright, this video is covering what we call probability models. This is basically a little bit more advanced probability, but a lot of the thinking that we've been talking about is going to be used here. So this should hopefully make a lot of sense. First off, when we talk about these two probability models, we want to talk about a specific type of probability, and this is a specific type of probability that can only be what we're going to talk about in this video can only be used under certain circumstances, and they're this. They actually call what we call Bernoulli trials. This famous that's Bernoulli. And I'm just going to start erasing that and do that over again. Anyway, this guy, Bernoulli, was a famous statistician. Bernoulli. And he created this whole idea, at least he kind of put it all together, not to say it's a rocket scientist, okay? And what a Bernoulli trial is there's kind of three major aspects. First off, in a Bernoulli trial, there are only two possible outcomes. That's it. Only two possible outcomes, and we label them as success or fail. So you're looking for either success or fail. That's it. It's not like there's 5 or 6 different things that could happen. We have just success or fail. And usually we call success P. The probability of success is P, and the probability of failure is Q. The second thing is that we have independent trials. And that's a good thing because that allows us to multiply. Independent trials says that the success of one trial will not determine the success of another. So what happens on one trial will not affect the next. So if I have a bunch of successes in a row, that doesn't mean success is going to be more likely or any less likely to occur because we have independent trials. And with independence comes the third thing, and that is that the probability of success remains constant. Probability of success remains constant. Remains constant. Meaning that if there's a 70% chance of success, then it's going to remain 70% for the entire problem. It's not going to change. And that kind of piggybacks off of independence. So with this whole idea of Bernoulli, we have, and again, these Bernoulli trials, what are these specific circumstances? We have two different types of models. One is very simple, and we have a name for it, but we very, very rarely refer to it by its name. And the other one is a really important one that we do use its name. So the first one, that again, we don't usually call it by name, but it's just really easy, to be honest with you, is what we call geometric model. Geometric model. And the second type of model we have is a binomial model. Now you will see this term binomial come up a lot. You might not see the word geometric come up a lot. Now in a geometric model, we're simply looking for the first success. And after that first success occurs, the problem's basically done. We only care about the first success. Binomial is a little bit more specific. We're looking for how many successes in n trials. Okay? We're looking for how many successes we could have in n trials. So geometric is just, first success, done. Binomials, when we say, okay, we're going to do 5 trials, how many successes could we have? Well, think it through. We could have none, 1, 2, 3, 4, 5. So it's a little bit more complicated when it comes to binomial. So to understand these two simple models, we're going to do a simple binomial or Bernoulli experiment here. And let's talk about a basketball player. Okay? And let's give this basketball player a name. Let's call this basketball player Bailey. Okay? And now Bailey, let's say when she steps up to shoot a free throw, she has an 80% chance of making a free throw. FT for free throw. Save me some time for writing it. Now let's assume, we have to assume independence. That means that every time she shoots a free throw, the probability is not going to change from 80%. So if she's, at the line in the state championship game and she's super nervous, and the pressure's on and she has to make the shot, still 80% chance. Or if they're losing by 20 and her making the free throw is only going to make them down by 19 and there's only 2 seconds left, so it doesn't really matter, still 80% chance. It has to remain 80% no matter the situation. Or maybe Bailey hits 15 free throws in a row. Well, guess what? On shot 16, she still has an 80% chance. It's not going to increase because she's on a hot streak or anything like that. All right, so basically we have two things that can happen. She either makes it or misses it. So we have success, and the probability of success we call P, so P would be 0.80. And then we have failure. Obviously, failure would be she misses the shot, and common sense tells us that that would be zero point 0.2. We call that Q. Q is failure. So we have P and Q. Okay? So let's say we're talking about a geometric model. Geometric means that we would ask a question like, hey, what's the probability she gets her first shot, her first shot made on the her eighth shot attempt? Okay, so notice that this is geometric because we're looking for her first shot attempt. Now this is actually really easy probability to figure out. So her first success, her first made shot comes on the eighth. That means trial 1, 2, 3, 4, 5, 6, and 7 must have all been failures. So I don't feel like writing out all those failures, so I'm just going to do 0.20 because that's failure, raised to the 7. That's 7 straight failures followed by a success. Okay? And that is very easy to think about. There's no other way that can happen. So it'd be 0.20 raised to the 7th times 0.8, and that's a very low probability. It ends up being 0.00001024, or if you move the decimal over twice, it's 0.001024%. So very, very small. Why is it so rare? Well, for crying out loud, Bailey's got an 80% chance of making a free throw. It shouldn't take her till her 8th attempt. So geometric probability is very easy. No one's trying to make it tricky. Another type of geometric probability question we could say is, what is the probability the first made shot is on second or third attempt? So her first made shot is going to be on the second or third. Okay, well, the second. What would it look like for her first make to be on the second? Well, that would be a miss, so one miss, right? Followed by, finally, on her second shot, she made it, okay? Or we also said, or the third shot. So the third shot would be 2 misses in a row, so 0.2 squared, 2 failures in a row, and then finally a success. And it would be one or the other, because the problem is saying we're looking for one or the other, so we would just add these two results together. So it'd be 0.2 raised to the first times 0.8 plus 0.2 raised to the second times 0.8. And I'm getting 0.192. And I think I did that right. I'm going to check my work real quick. I believe so. So she's got about a 19.2% chance of making her first shot on the second or the third. So those are the types of questions you could ask. Watch out for the tricky type of question where we would say, what's the probability she makes it on her first shot on fewer than 3. So that would be fewer than 3 means the first or the second. Fewer than 3. Didn't say 3 or fewer, it said fewer than 3. So the first or the second. So that's it. You're looking for that first shot, and you're trying to find out what the probability of it happens. Very, very simple geometric probability. We usually don't even refer to it as geometric because it's just such common sense. Now let's look at some binomial examples with this. A little bit trickier here, and this is where we got to do a little bit of discussion because binomial is a lot trickier. But it's not really that hard once we get it figured out. So now binomial, we would say something like, okay, Bailey's going to shoot 5 shots. Okay, so now I'm giving you how many trials she's doing. I'm not just looking for the first trial or the first success. I'm telling you she's shooting the shots 5 times. And I will know the probability she makes exactly 2. So she makes exactly 2. Now, the issue with that is obviously that's going to be 2 successes. And that's going to have to be 3 failures. Because again, it said she's shooting 5 shots. So that's going to be 2 successes and 3 failures. But the order of those matters. It could be different. So let's try to see if we can make a list of all the different ways here. So she could maybe I don't want to use M's for makes and misses. So let's do just S and F for success and failure. So she has success success, fail, fail, fail. So she made her first two and then missed them. But that could also, maybe she would do this. Makes her first one, fails, success, fail, fail. Maybe she could do success, fail, fail, success, fail. Success, fail, 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 success. And I don't even know if there's probably more out there. Let's think. She can miss the first, make, miss, miss, make or miss, make, miss. I mean, this list might go on for a while, and when I'm all done, I might be like, how do I know I'm done? Did I forget one? I don't know. So we need to find a way to figure out all these different options because there are several different options. But before we talk about that, I want you to know that all of these options, however many they are, they all involve two makes, so two successes. Successes, point 8. They all involve two successes, and they all involve three failures. No matter what, every one of these involves two successes and three failures. But the problem is that it can just happen in so many different ways. It could be the first two, or the first and the third, or the first and the fourth, or the first and the fifth, or the second and the third. So there's all these different options, and technically all of them look like this. I mean, all of them look like this right here, but I would have to add up all those options together. And I don't feel like listing them all. Again, I don't even know if I've got them all, and I'm nervous that I might forget one. So we have a way, using our calculator, that we could have the calculator do this for us. Here's the notation. The notation we use is actually kind of back from, you might have learned it in pre-calculus potentially, but it's based on combinations. So we have 5 events, 5 trials, and we're looking for 2. So this is the way we write it down, 5, choose 2, okay? So on our calculator, we do 5, choose 2. And you might remember this back from possibly even geometry when you learned about this. So we have 5 and we're going to choose 2. Now the formula for this, by the way, the formula for this, and I'm going to give you the formula, but we're never going to use this calculator, will do it for us, is 5 factorial divided by 2 factorial times 5 minus 2 factorial. Very ugly, but wait a minute. I'm going to teach you how the calculator can do it. Okay, using our calculator, the first thing you do is you type in how many trials you have. So you can type in 5 trials. Then you go math, slide over to PRB for probability, and come down to the number 3, which is NCR. That stands for choosing. So I'm going to do 5, choose 2. Now you got to type the 5 in first. That's the N. R is the 2. Now, I don't know why they call it an R. It's really how many successes you're looking for out of 5. So we're looking for 2 out of 5. So we hit enter, and that tells us there's 10 different ways that this can happen. 10 different ways. So if we go back here, I've listed, let's see, I listed 6 of them. There must have been 4 more. I forgot. I'm sure I could figure them out if I took the time. But the point is, I don't want to take the time. I want the calculator to do that for me. So there's 10 different ways this can happen, and I'm going to multiply that by every one of those 10 ways. Looks like this: 2 successes and 3 failures. So that is how I'm going to get my answer. So it'd be 10 times 0.8 raised to the second times 0.3, I'm sorry, 0.2, excuse me, sorry, raised to the third. And we get 0.0512. So she has about a 5% chance of making 2 out of 5 shots. Why is it kind of low? Again, she's an 80% free throw shooter. She should be making more than that. So the key thing here is, let's kind of make out a formula for binomial probability. The formula is you're going to have n trials, and you're going to look for x successes, okay? And you're going to take P, and you're going to raise it to how many successes you want, because I wanted that many successes. And Q would be raised to the n minus x, and that would be how many failures you're looking for. So in our last example, remember we were looking for 5 shots. We wanted 2 successes. So we did success, 0.8, and we squared it because we wanted 2 successes. And then 5 minus 2 would obviously be that we wanted 3 failures. So that's where we came up with this formula. So this is the formula right here that you're going to use for binomial. But be very careful. This first part right here just tells you how many different ways it can happen. Use your calculator to do that, please. It'll make your lives so much easier. Okay? All right, so now what we're going to do is we're going to take a look at a couple examples that deal with binomial probability. Here we go. A manager notes that there is a 0.125 or 12.5% probability that any employee will arrive late for work. What is the probability that exactly one person in a 6-person department will arrive late to work? So again, I need one person to be late for work, exactly one out of 6. So that's going to be, I need one success. Now, success would be being late to work. I don't know if that's a success, but in terms of how the problem would be worded, that would be my success. And I need one person to be late for work, and I need the others. So that'd be 1 minus 1.25. That'd be 0.875 would, I guess, be the chance that you are on time to work. I need 5 of those. There's my total of 6 people. I need exactly one person to be late, the other 5 to be on time. But that could look so different. That could be, okay, success meaning late, and then fail, 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 fail. Or obviously I could have this person be on time and then this person be late, fail, 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 and so forth. So, the idea here is I'm going to use the formula that I'm going to have my calculator help me with this. I have 6 people. I need to choose exactly one of them to be late. My calculator is going to help me get that number. Again, I'm going to type the 6 in first, math, PRB, slide down to NCR, and I'm going to choose 1. Now, actually, this is pretty easy. It's 6. Hopefully, you would have known that it's 6 different ways you could have one person. First, second, third, fourth, fifth, sixth. Okay, not rocket science there. So there's 6 different ways that can happen. All 6 of these ways have 1 success, which is being late to work, and 5 failures, which is being on time to work. So kind of opposite there thinking, but it's because of what the problem is. So we have 6 times 0.125 times 0.875 raised to the 5th. So there is, the answer here I got is 0.3847. 3847. So there's a 38.47% chance that at least one person will be late to work. What about exactly 2 people out of the 6? Okay, so now we have 2 people being late. Okay, so we got 2 people being late, so 2 successes being late. And then we got 0.875, that'd be failure, being on time, gosh forbid. And I need 4 of those. There's my total of 6, 2 people on time, 4 people late. And I need to figure out how many different ways that can happen. So I have 6, choose 2. And again, I like to just kind of run through them so you get the idea. That could be late, late, on time, on time, on time, on time, late, on time, late, on time, on time, on time, late, on time, late, on time, on time. And I don't feel like figuring out all the options. That's where my calculator comes in handy. So I'm going to do 6, math, PRB, NCR right there. Choose 2 of them, and it's going to tell me how many different ways it can happen. There are 15 different ways you could have 2 people out of 6 be late. And now that's going to make my work a lot easier because I certainly do not feel like sitting around and figuring all those out. So we got 15 times 0.125 raised to the 2nd times 0.875 raised to the 4th. And that gives me, I'm checking my work, 0.1374. 0.1374. You might say, well, why is it so much lower? Well, think about it. It's pretty, not to say rare, but it's unlikely, 12%, it's unlikely for somebody to be late. So for 2 people to be late, it should be fairly unlikely. Okay? All right, let's check out this other one here. Here's a really good type of AP type question. A manufacturer of cameras has the following quality control check at the end of its production line. Quality control means a way of checking to make sure that the cameras do in fact work. Here's the deal. If at least 8 out of 10 randomly picked cameras pass inspection, then the entire shipment for the day is approved. If at least 8 out of 10 randomly picked cameras pass inspection, then the entire shipment for the day is approved. It is known that approximately 85% of cameras pass inspection. What is the probability that a shipment will make it through inspection? Okay, so first we have the probability of P. Success appears to be 85% chance that a camera passes inspection. Failure Q would be 0.15. Okay, now here's the key. At least 8 out of 10. Okay, at least 8. That means 8 or more. So please be careful. That means 8 or more. Okay, and that means 8, 9, or 10, right? Because it said out of 10. So 8, 9, or 10 would be 8 or more, at least 8. So we got to get all that straight. So we have to do this problem 3 times and then add all the results together because it could be any one of these results. Okay, so first we would have 10 cameras. We need 8 of them to be successful. That would be 8 successes, 0.85 to the 8th, and then we would need, let's see here, 2 failures. So there's our 10 things that are happening. What is this right here? This is just going to tell us how many different ways that can happen. So we could have pass, 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 fail, fail, or there's many different ways that can happen. But we could also think about the fact that we have at least 8, means 8 or more. So we could have 10, choose 9 of them to be successful. That would be 9 successes and 1 failure. Or we could even have all 10 and choose all 10 of them be successful. Now we're going to have the calculator do this, but how many different ways can you have all 10 be successful? 1. So you should know that's 1, but we'll show the calculator. We'll tell us that anyway, just in case. So we got 10 successes and we have 0 failures. Now hopefully you remember that anything raised to 0 is 1, so that's not really going to play a part in here, but it's good so you see it. So we have 8 successes, 2 failures, or 9 successes, 1 failure, or all 10 successes, no failures. And again, I have to figure all these out and add them together because the problem did say at least 8, and that means 8 or more. So hopefully you guys understand that. All right, so here I go. The first thing I do is I got to figure out what is 10 choose 8. So 10 math. I guess got to slide over to PRB. NCR choose 8. Okay, how many different ways that can happen? Holy cow, 45 different ways. We've never thought that. So, and I certainly would not want to list all those out. So we got 45 times 0.85 to the 8th. Times 0.15 to the second. Okay, how about 10 choose 9? And I'm just going to go second enter to pull that back up and change that 8 to a 9. Saves a little bit of time there. Okay, only 10 ways that can happen. Okay, that's not too bad, a little bit less. 10 ways, that'd be 0.85 to the 9th times 0.15 to the first. Okay, and then finally, like we said, we should already know what this is. We really should. Should make sense. 10 choose 10 would be 1, but you never know. Okay, so there it is. Okay, so we do know that there's only one way you could have 10 successes out of 10. So that'd be 0.85 to the 10th, 0.15 to the 0. So I got to figure all these out now. So 45 times 0.85 raised to the 8th times 0.15 raised to the second is 0.2759. 0.2759. And let's see here, 10 times 0.85 raised to the 9th times 0.15 to the first. And that is 0.3474. 0.3474. And one more to go here. 1 times 0.85 raised to the 10th times 0.15 to the 0, which I know is 1. And that is 0.1969. 0.1969. So I'm going to add all those up. 0.1969 plus 0.3474 plus 0.2759, and I get 0.8202. So the total of all of these here is 0.8202. So that means that on any particular shipment has an 82% chance of passing and going through inspection. That's because I have to have at least 8 out of 10 cameras be chosen, and at least 8, meaning 8, 9, or 10, have to be successful for me to pass that shipment on as an okay shipment. That means the opposite of that would be 1 minus 0.8202. That means there's about a 17, or if you just want to round it, 18% chance that it gets rejected. And that would mean we would have 7 or less. So 7, 6, 5, 4, 3, 2, 1, or no successes. All right? So hopefully that makes sense. All right, let's take a look at this problem here. Joe DiMaggio had a career batting average of .325, 32.5% chance he'd get a hit. What is the probability that he would get at least 1 hit in 5 official times at bat? Now, I like this phrase, at least 1. At least 1 is easy for me. At least 1 means 1 or more. So this would mean that he has 5 hits, he gets 1. Out of 5, he gets 2. Out of 5, he gets 3. Out of 5, he gets 4. Or out of 5, he gets 5. Now, we just saw in the last problem that doing 3 of them takes quite a bit of time. This time, they want me to do 1 or 2 or 3 or 4 or 5. They want me to do 5 cases. Now, I'm going to teach you a little bit of a shortcut that you can do under certain circumstances. Notice I said he gets 1 hit, 2 hits, 3 hits, 4 hits, or 5 hits. The only option I didn't mention is no hits. So if I do 1 minus the probability of no hits, I will get everything else, because in this case there's only 6 options. No hits, 1 hit, 2 hit, 3 hits, 4 hits, 5 hits. They're asking me to find these. They're asking me to find the probability of at least 1, meaning 1 or more. So if I just get rid of no hits, I'll have my answer. So what would no hits look like? Well, that would be 5 at-bats, no hits, and that would be 0.325 to the 0. No successes whatsoever. And failure would be 1 minus 0.325, obviously, 0.675. So it would be 0.675 to the 5. All 5 no hits. Now, we should know there's only one way that you could have 5 with none. It's all none. There's only one way that could happen, but we will show that real quick. It'd be 5, math, sign over to probability, NCR, choose none, and there should only be one way that could happen. Yeah, that makes sense. So we have 1 times 0.325 to the 0 times 0.675 to the 5th. So basically, I really can just do 0.675 raised to the 5th, because 1 is 1, 0.325, anything raised to 0 is 1. So I get 0.140. Now that's the probability of no hits, 0.1401, excuse me. And I got to do 1 minus that to figure out what I'm looking for. He gets at least 1 hit, means 1 or more. So subtract that away, and that means there's, out of 5 at-bats, there's a 0.8599. So pretty close, about an 86% chance that he's going to get at least 1 hit out of 5 at-bats. And again, that's at least 1 out of 5, meaning 1 or 2 or 3 or 4 or 5. So that's kind of a shortcut to do it, as opposed to doing all 3 of those like we had to do on that one. Alright, last problem here for this video. If the probability that a male birth will occur is 51%, what is the probability that a 5-child, sorry, a little typo there, a 5-child family will have all boys? What about 4 boys, 3 boys, 2 boys, 1 boy, or all girls? So basically I want to make a chart here. So I want to talk about, okay, they have 5 kids. What's the probability that they're all 5 boys? 4 boys, which would mean 1 girl, obviously. 3 boys, which would mean 2 girls, obviously. And 2 boys, which would mean 3 girls, obviously. 3 boys would mean 2 girls. 2 boys would mean 3 girls. 1 boy, which would mean 4 girls. Or you could have no boys. Okay, no boys, which would be all 5 girls. Okay, that would be all girls. So we're going to make what we call a probability chart, or a probability model. A probability model is what we're going to really spend a lot of time doing next. And that is the fact that you list all of your outcomes. You want to list everything that can happen. And right next to it, we're going to find the probability of each of those. Okay, that's a probability model. What could happen, and what are the probabilities of them? So let's see here. So 5 boys, so that'd be 5 boys, or 5 kids, choose all 5 of them to be boys. That would be 5 success, so 5.51 to the 5th, times 0.49, that'd be the chance of having a girl, obviously, to the 0, none of those. 4 boys would be 5 kids, 4 of them are chosen to be boys, 0.51 to the 4th for the 4 boys, times 0.49 to the 1 for the 1 girl, obviously. Or we could do 5, choose 3. This would be 0.51 to the 3rd for the 3 boys, 0.49 to the 2nd for the 2 girls. 5, choose 2. This would be 0.51 to the 2nd, times 0.49 to the 3rd for the 3 girls. And we have 5, choose 1, 1 boy, so that'd be 0.51 to the 1st for the 1 boy, 0.49 to the 4th for the 4 girls, and then finally 5, choose no boys, so that'd be absolutely no boys, 0.51 to the 0, no boys, 0.49 to the 5th for all girls. So you'd actually have to go through and figure out all these out. And I'm going to try to do so fairly quickly on my calculator here. 5 choose 5. I know that that's 1. There's only one way that could happen. So it'd be 1 times 0.51 raised to the 5th. And then I don't even need to type in, but I'll do it anyway. But I really don't need to type this in because anything raised to 0 is going to be 1, so it shouldn't matter. And I get 0.0345. So the probability of having all boys is 0.0345. 0.0345. All right, then you're going to go through and do the rest of these. Hopefully you can do it along with me here. I'm going to try to move fairly quickly, and I'm going to do this on my own calculator here so I can get through it. There's 5 ways you could have 5 choose 4 times 0.51 to the 4th times 0.49 to the 1st. I'm getting 0.1657. And hopefully you're doing this along with me so you can choose. So 5, choose 3. Okay, that's 10 different ways you could have 3 boys out of 5 times 0.51 to the 3rd times 0.49 to the 2nd. So there's a 0.3185. 0.3185. All right, finally we got 5. 5 choose 2. That's 10 different ways that can happen as well, times 0.51 squared times 0.49 to the 3rd. And we get 0.3060. 0.3060. All right, moving on here, we got 5 choose 1. There's only 5 ways that can happen. That should make sense. 5 choose 1. There's 5 ways that can happen. 5 different boys. 1st, 2nd, 3rd, 4th, or 5th. Times 0.51 to the 1st times 0.49 to the 4th for the 4 girls. 0.1470. And finally, we got 5 choose no boys. There should only be one way that can happen. All girls, no boys, right? There should only be one way that can happen. Times 0.51 to the 0. I really don't need to be typing that. Times 0.49 to the 5th. And I get 0.0282. 0.0282. Now here's the thing. This is a complete set of everything that can happen with 5 kids. So all of this, a good way to check is all of this should add up to 1. So 0.0282 plus 0.1470 plus 0.3060 plus 0.3185 plus 0.1657 plus 0.0345, and I get 0.99999. So pretty close to 1. It's probably off a little bit because of rounding. So it's a good way of checking that you can figure this out. So hopefully that makes sense. Binomial. Don't forget about geometric. Geometric, we usually don't talk about too often because it's so easy. If I say, what's the probability of your first boy on the 3rd kid? Okay, first boy on the 3rd kid. So that's no boy, 3rd kid. So I need 2 of those. No boy, and then finally I have a boy. Right? That's the only way I can happen. So it's fail, fail, and then success. Now, what about the other 2 kids? Who cares? I didn't even mention them. I just said all I'm looking for is your first boy on the 3rd child. So that would mean girl, girl, and then boy. So, again, fail, fail, be girl, girl, and then boy. There's only one way that can happen. I don't have to worry about anything else there. It's pretty easy. So that's geometric. So watch out for those. Be careful when you see the word at least or at most, because that you have to think at least means more than, at most means less than. Please really think those types of problems through. All right, that's it for binomial and geometric probability. Hopefully it makes sense. It is fairly easy.